Hey guys, this is Heidi talking, and with Milan and Ari, we wanted to tackle a topic that sounds complicated but is actually something we see all the time: thermodynamics. So, what is it exactly? Let's go Greek for a second. Thermo means heat, and dynamics means movement. So, thermodynamics is about how heat and energy move around. So, we study how energy transforms into some kind of work or heat, showing that the three are linked together. Then, when it comes to thermodynamic systems, we use them to analyze matter inside a boundary. Also, we don't track every particle, but treat it as a whole thing. As for boundaries, we add them to focus our calculations, and they could be existent or imaginary. Since this is a brief intro to the subject, we aim to tickle your curiosity without telling you everything about systems. But what a better way to explain this subject than with the laws of thermodynamics? So, long story short, there are four laws. First came the first law, then the second law, and the third. But what about the fourth one? Even though this was the last officially discovered, its understanding is fundamental for the other laws. But first law was already taken, so they named it the zeroth law of thermodynamics. And what is this law about? Basically, if a system A is in thermal equilibrium with a system B, and this same system B is also in thermal equilibrium with a system C, then A and C are in thermal equilibrium between each other. That makes temperature measurement possible. So, for example, we have a sofa, system A, and the environment, which is system C. A is in thermal equilibrium with C. Then we also have a coffee in the room, system B, which is still hot, by the way, and this coffee will cool down, so lose heat, until it's thermal equilibrium with the environment, so system C. Now C and B are in thermal equilibrium. Therefore, A and B are also in thermal equilibrium. Now let's go further with the first law.
Let's imagine that I record myself holding a ball, then it's decided to just throw the ball and now I can't see it anymore in the frame. Does that mean that the ball does not exist anymore and that the energy I exerted onto the ball disappeared into thin air? Not exactly. This is very much like the first law of thermodynamics. Essentially, it stipulates that energy cannot be created nor destroyed. Even if it appears that the energy was lost, realistically it was transformed into another form. When the ball hits a surface, it absorbs some of the ball's energy, while some energy is also lost to sound.
Second law of thermodynamics. The second law is when entropy dictates if a process or a reaction is going to be spontaneous. The total entropy, or the disorder of an isolated system, will always increase over time or remain constant in ideal cases where the system is in equilibrium. It essentially means that natural processes tend to move towards greater disorder and energy dispersal. Energy naturally spreads out and disperses if not actively constrained. This principle governs many natural processes, from heat transfer to chemical reactions. The entropy always increases. In an isolated system, the total entropy never decreases. For example, the heat flows from a hot to cold system. So, the energy spontaneously transfers from a hotter object to a colder object until the equilibrium is reached. The entropy is very similar to this as well. Some examples of entropy include melting ice. An ice cube melts in a warm room because heat naturally flows into it, increasing its entropy. Another example is burning wood. Combustion converts structured wood into ash, heat, and gases, increasing its disorder. The last example can be heat engines. No heat engine or any engine can be 100% efficient. Some energy is always lost as waste heat.
We can imagine the third law of thermodynamics as an analogy for a student going through a semester. On day 0 of the semester, there is very little work to do and the level of organization is pretty reasonable. As time goes on and we get further away from day 0, the amount of work that needs to be done starts to get chaotic. This is pretty analogous to the third law of thermodynamics. We can think of the entropy as being a measure of the disorder and spontaneity of a system. The closer we are to the absolute temperature in Kelvin, the closer we are to the entropy being closer to 0.